Okay, these are the basic reaction types. Of course, all reactions have reactants and products. All reactions go from unstable to stable, but there are different configurations for reactions. And these are the major four. Synthesis, A plus B gives you AB. In other words, you're putting stuff together, synthesizing. And when you get to 2B or to your OChem STEM class, you're going to be doing lots of synthesis, basically making stuff. An example is how you make water. Make water a number of different ways. One way is taking hydrogen and oxygen, putting them together, and they make water with a lot of energy being given off. This is what they use frequently for rocket engines. Liquid hydrogen, liquid oxygen. And when they go together, a rocket, a big giant rocket, goes up. There's that much energy when you make water because water is really stable. Now, hydrogen gas and oxygen gas are also stable, just that when you put them together, it makes a more stable compound. Okay, the opposite of synthesis is decomposition. So we can take water apart, just like we put it together. We end up with hydrogen gas and oxygen gas. There's something called single replacement. That's what our lab's going to be about today and tomorrow. And that's where you start with a metal and a salt, and then something happens to the metal. The metal becomes a salt, and the salt becomes a metal. For example, if we put copper and silver together, what happens is we have the copper goes from metal to the salt. When I say salt, that's ionic compounds. Table salt is a good example of millions of different salts in the world. Millions. This salt here, the silver, becomes a metal. Now, single replacement reactions involve electron transfers. Okay, electron transfers between the metal and the cation. Now, the anion just kind of tags along. I'm going to give it a special name. But the action is with the metals. So single replacement reactions are electron transfers of the metals involved. One loses, one gains. Okay? And we're going to go into depth on this reaction today. Another very common reaction is called double replacement. We have single, we have double replacement. With a single replacement, you're just talking about metal to metal solid. With double replacement, we're swapping kind of everything out. So if we start with like this here, we have silver nitrate and sodium chloride. So what happens is the silver goes to the chloride and let's see, let me redo this here. Silver goes to the chloride, and then the sodium goes to the nitrate. Yeah. Okay, his question had to do with apostrophe. Notice there's a double apostrophe and a triple apostrophe. What that means is when I say salt and then say salt again, how do you know they're different? One has an apostrophe, one doesn't. One has two apostrophes, which is different than the other two. One has three apostrophes, which is different than. That's frequently you'll see that in chemistry and physics.
What that mean?
Huh?
It doesn't mean nothing.
It means they're different.
Okay.
Yeah, that's all. In other words, silver goes to silver chloride, forms a new salt. That would be the salt prime. The sodium goes to the nitrate. That would be the salt double prime. Just that they're not the same anymore. That's all it means. And it's used a lot in science. Not so much biology, but frequently in the physical sciences, chemistry, physics, geology. Geology has a ton of chemistry, and engineer uses a lot. Okay, so the question now is, do they stay an ion or not? Yeah,
So, see where so it says NaCl8P. With the. Oh, and then what's under it? I'm sorry, that would be,
these guys here.
no, the one next
Yeah.
is AgCl15, or is that in the,
On the right?
yeah,
Oh, that's S for solid,
oh, gotcha, okay.
parentheses. That's
No, okay,
it's a crappy looking parentheses.
I was just confused because I thought it was an AQ. And I thought. I got mixed up between the NaClHQ and then it says AgCl, so I didn't know if it was.
Yeah, but Tomorrow, I'm going to talk a lot about double replacement. And you're going to see what that S, what does that mean
Gotcha.
versus AQ.
Gotcha.
Okay, so basically double replacement is we swap out either the cations or we swap out the anions. Not both, just one set or the other set. And then we have to make a determination whether solid forms with that new swap or not. And I've got it, and there's no way to predict that either, by the way. So you need rules, solubility rules, or a table. And I'll be giving you both of those tomorrow. Okay, so today we're going to focus on single replacement. This reaction here. Okay, so I mentioned a few minutes ago that when a single replacement reaction is electrons being transferred. When electrons are being transferred, that's called oxidation. The thing about electrons being transferred, they've got to go someplace. The recipient of that transfer is called reduction. So oxidation means electrons are leaving. Reduction means electrons are being received. And they frequently abbreviate this as redox. Redox reactions. So we have reduction, oxidation, redox. Now, they have to happen together, no exceptions. The reason why there are no exceptions, you just can't have free electrons roaming around. It's called a free radical. Free radicals are extremely unstable. So for them to become more stable, they just immediately combine with something, whatever's closest to them. So it's totally unplanned. That's why you have to have a willing recipient for those electrons. So it's a stable reaction. Iron does what when you spray it with water? All of you have experienced this. Rust, right? That's a single replacement reaction. Because the iron goes from shiny iron to a salt. Rust. Ferric oxide is a salt. Okay, so what we're going to do now is we're going to take those two reactions apart. One where the electrons are leaving, the other electrons are being received. Those are called half reactions. So let's look at copper. Copper forms a very stable ion, copper 2. Copper 2 means it's got a charge of +2. +2 means it's 2 electrons short of what it was when it was a metal. Now, in my class, I always write metals with a 0 superscript to indicate there's no charge. No charge means it's a metal. So here we go, copper 0 going to copper 2. Difference there is 2 electrons. So when copper goes to copper +2, it gives off 2 electrons. Well, what's going to receive it? The silver is going to receive it. So, potential spam. Getting this all morning. Take that. Okay, so the recipient is going to be the silver ion. So it's going to, and the silver ion is a +1. So how many electrons can it receive? 1. So we have to have 2 silver ions to receive the 2 electrons being given off by the copper. And each one of those is a half reaction. Now, half reactions are half of the reactions, not the whole thing. So we need to put those 2 half reactions together to make the whole reaction. So what's got to cancel when we add those 2 up algebraically are the electrons. So we have 2 electrons here. We have to have 2 electrons on the other side of the equation. So they cancel, which is a fancy way of showing the one is is leaving and the other is being received. Okay, so this is crucial to show you what's going on. Half reactions are also out of the scope of this class, but I like to talk about them because it really shows what's going on internally. So you'll get half reactions in your next class, and they will think you've never seen them before. Okay, when we algebraically add these 2 together, now we had to double the silver reaction because we had to get the number of electrons up to match the other one. So we add this up, we end up with here. Now, what have we not included here? The what?
The 2 electrons.
We did account for those because we showed how they cancel and we add the 2 half. But that's good. Keep thinking that. What else? Huh?
The night.
The nitrate, the NO3. The NO3 is just riding along joyfully, nothing happens to it. When you have an ion that doesn't participate in the reaction, it's called a spectator ion. We're going to see this tomorrow as well with double replacement. Spectator ions, just like when you go to a ball game, if you're not the player, you're a spectator. You don't hit the ball, you don't catch the ball, you don't do anything. You just watch. That's what spectator ions do. They don't participate at all in the reaction. If they change at all, they're no longer a spectator ion. By definition, spectator ions have to be unchanged through the process. It's not in a way, it's exactly what it is. Yeah, exactly. Okay, so we have to add those in before we're done here. Because right now we've just got talking about cations, not, that's a 0, by the way. Okay, so we have to add the spectator ions. In this case, nitrate, if you look on your common ion chart, is a -1. So when we pair that up with silver, it's going to be AgNO3. 1 nitrate, 1 silver, +1, -1. And pair it up with the copper. When copper goes from a metal to an ion, it's a +2 charge. We need 2 nitrates to balance the +2 charge. So adding in the nitrates, this is our reaction. Okay, now the question now is, are the products more stable than the reactants? To answer that question, you need a chart that shows that. This is the one from your lab today. This is called a metal activity series. At the top are the most reactive. The bottom are least reactive. Now let's look at the very bottom one. AU is gold. Does gold ever turn to a salt on your finger? No, that's because the metal is very stable. That's what this says here, the very bottom. The very top, we have lithium. All of you have heard of lithium because of batteries. Lithium's at the very top. That means it doesn't like to be a metal. It likes to be an ion instead, big time. So this process here you're looking at is called what? Oxidation or reduction? Why oxidation? Losing electrons. By definition, that's oxidation, yeah. So this is also an oxidation series. So the reactions at the top want to be oxidized more than the reactions at the bottom. Okay, that's key to understand. So to answer the question, this reaction over here, we need to find copper and silver on the reactive chart. Okay, notice the copper is at the top, silver is at the bottom. So copper wants to be oxidized more than silver. So what you do. What you do with a reaction like this is you find the metal. Copper. Is copper above or below silver? Above. So this reaction happens. That means copper wants to be oxidized. So what happens is it jumps over here and is oxidized. So step number one is identify the two metals on the reactivity chart. Which is above the other one? If the metal is on the top, the reaction will happen. If it's reversed, there'll be no reaction. So this reaction will go. We throw silver and copper together. What happens is you'll see this reaction in lab today. It's really cool. I'm going to take a copper wire, spiral it. I'm going to put some silver nitrate solution around it. And within minutes, you're going to start seeing silver forming. It's really cool. And what happens is it's very, very pretty in the beginning. And then after a while, the silver metal starts to tarnish because there's sulfur around. What happens? That's when silver gets very dark. That's silver sulfide. Okay, so again, find the two metals on the reactivity chart. If the metal, in this case copper, is on the top, it goes.
Without. Like, our answer. Down that way, that would be our answer at that.
On the test, I'm going to ask you, will this reaction go or not? One, you need to identify single replacement, copper and salt. If it is copper salt, I'm going to give you a reactivity chart. The one from your lab is the one I'm going to give you for the test. And then you're going to find the metal on the reactivity chart, and the metal's above the other one, it goes. And you'll say yes. And the second part of that question is why? Those were 10 points, 2 points for yes or no, and 8 points as to the why. Same thing with a double replacement. I'm going to give you a double replacement reaction. I'm going to say, does anything happen? And when I say anything happen, I'm talking about is a solid form. Okay, all right. So in lab, you're going to be making these predictions. So let's look at this one here. We have iron metal, iron 0, with aluminum sulfate. Does anything happen? Okay, we're going to find iron and aluminum in our reactivity series. And aluminum. Okay. Aluminum is on top, but we're not starting with aluminum metal, we're starting with iron metal. So, right, no reaction. Now, I wrote, instead of NR, I wrote NVR. V stands for visible, no visible reaction. Now, the reason I put the V in it instead of just saying NR is we're going to be working with acids as well. Okay. By definition, an acid disassociates H plus. If H plus disassociates from what you're starting with, it's by definition an acid. There are other definitions of acids too, but that's the most common one. And they always start with that example. And they get into the little refinements and stuff. Okay, so if you have, instead of a metal in this reaction here, you've got hydrogen. Acting as the metal. And H plus acting as the salt, cation. So you'll be working with acids today and tomorrow. Mostly sulfuric acid, H2SO4. Everything else is a metal, except for the H2, 2H plus, 2 electrons. Now, as you know, cations can be multiple charges. All the charges we're working with today and tomorrow are +2. So you'll see this, except for, well, a couple of them are +2. Most of them are +2. Like silver doesn't make a +2 ion. It only makes a +1 ion. So you can't show that, but okay. So this is a definition of an acid. Dissociates H plus. Now, a lot of compounds have H's in them. Not all of them are acids, though. Some compounds, like acetic acid, has H's that don't dissociate and H's that do. If any of them dissociate, it's an acid, regardless of how many don't. For example, fatty acid. Most common fatty acids are 18 carbons long. And one of those H's, every carbon, remember, on the end is going to have 3 and in the middle is going to have 2. So if you've got so fatty acid, this happens to be stearic acid found in pork and beef. Stearic acid has got 3 plus 32 plus 2 plus 1. So what is that? That's 30, 38 hydrogens. Only one comes off of the 38. Only one. Yep, it's an acid then. Some acids have 2 coming off, like sulfuric acid. Some have 3, like phosphoric acid. Or citric acid, it's got 3 also. Oxalic acid, found in spinach, it's got 2 come off. So it varies. Bottom line is, did an H plus come off? Yes or no? If it's yes, it's an acid. No simple question. Now, later on, we're going to talk about there are strong acids, weak acids. What's the difference between the two? I'll talk about that when we talk about acids in more detail. Okay. So acids will come into play, and the H plus is the part that's going to come into play specifically. The H plus. Okay, so let's do some more examples here. You're going to do lots of examples in lab. Okay, so let's look at this one here. Okay. We have potassium metal and aluminum sulfate. And aluminum sulfate, salt now, we're gonna put an AQ. Now we know that's a salt. As soon as the AQ is on there, that means it's dissolved in water. Hence AQ. If it's S, not dissolved in water, it's a solid, not dissolved in water at all. Because the crystal lattice force is greater than the solvating force in that water. Okay, first of all, is this thing balanced? No, not balanced at all. So let's balance it. Okay, we've got a K, aluminum. I'm going to put the sulfate as an X. And we've got one potassium, two potassiums, two aluminums, one aluminum, three sulfates, one sulfate. So it's not balanced at all. It's awful. So let's balance it now. Look at the most complicated ones first. That would be the aluminum sulfate and the potassium sulfate. We got three sulfates on the left. Let's make three on the right. That makes six potassiums on the right. So what do we want to do now? Okay. Same deal with aluminum. Okay, we're in good shape now. Now we've got the situation, we've got a metal and salt. Salt. Single replacement reaction. Is it going to go or not? So we've got potassium up here and aluminum down there. So the potassium metal is above the aluminum ion. So this definitely is going to go. Now, potassium is way at the top. So you don't even have to look at the reactivity chart to know that that's definitely going to go. In fact, up at Hanford in Washington State, they have a process that makes sodium metal and potassium metal. And they had to get rid of it. So what they decided to do was to throw it in a lake. And they threw in so much potassium, metal, and sodium metal that the lake boiled. The lake boiled. It was quite the deal. And they got in trouble for doing it. EPA said, bad, bad, bad. But they did it anyway. So potassium metal, sodium metal, both of them are very, very, in fact, when you buy this, it comes under oil. So there's no water vapor close by. Very, very reactive. Okay, so this reaction definitely goes. What's the spectator ion? Sulfate, SO4. Nothing happens to it. So I will always ask you, your lab doesn't ask it, but I will always ask it on a test. If the reaction goes, what's the spectator ion? So make sure you identify that. Double replacement reactions, we're going to see tomorrow, same question. What are the spectator ions? Now with single replacement reaction, there's only one spectator ion. Double replacement reactions, there are sometimes 4, sometimes none, sometimes 2, it varies. So it's from 0 to 4. But single replacement reactions always, no exceptions, always have 1. Okay, so this is starting to click in terms of looking at the reactivity series and where the reaction is going to go. Metal, find the metal. Is it on top? Yes, it'll go. If it's on the bottom, no. So let's do one with an acid. Let's take, oh, I know. When I got married the second time, this friend of mine has a really fancy house in Napa. And she was an artist. She used to make metal sculptures out of sheet iron. And she cut them out with a cutting torch and weld them and do all this fancy stuff. And then she sprayed them with hydrochloric acid. So what do you think that did to the iron? Rusted the heck out of it. And that was part of her deal. It was a really cool yard. She must have had 15 of these sculptures, the size of this table. It was really kind of cool. Okay, so let's do that reaction. Okay, so we're going to have iron metal. That's hydrochloric acid, HCl. You already know what's going to happen. So we're looking for the H's and the ions on a reactivity chart. So here's the H and here's the iron. So iron is above the H, so it goes. And we could have predicted that. So in our reactivity chart, the iron is going to be iron 2. Iron 2. So iron 2, what's the charge on iron 2? Plus 2. So that means we need 2 chlorines at -1 apiece. Okay, is everyone okay so far? Okay, is this balanced? No, it's not balanced. Okay, so we've got some issues here. We have, let's just write all this out, FeClH. Okay, 1 iron, 1 iron, 1 H, 2 H's, 1 Cl, 2 chlorines. Okay, so if we put a 2 in front of the HCl, that'll kick that up to 2, that up to 2, and we're done. Always make sure your reactions are balanced. Okay, in case of rust, what happens is this would then undergo another reaction with oxygen and it forms rust. It's like a secondary reaction. That frequently happens in nature. You'll make one thing and all of a sudden it changes to another, which is more stable. So the rust is more stable than the iron chloride. Iron chloride isn't all that stable either. They use it in the electronics industry to actually take copper off of boards after you're done. they use ferric chloride wash to take the copper off. So it's pretty reactive. That's why it reacts pretty fast with oxygen form rusts. Okay, how do you guys feel about single replacement reactions? Now you're going to practice it a lot in lab today and tomorrow. So what I want you to do is when you do the reaction, you can do it in a spot plate. I want you to predict whether it'll happen or not. Predict, then do it. Now the only problem is, if it's a neutralization reaction where you have an acid and a base, the reaction you're not because it's going to make water. So you're going to make water in a water solution. That makes sense or not? So you're not going to be able to see the product. So you're going to write no visible reaction. No visible reaction. Reaction happened, you just can't see it. Okay. All right, let's do another one here. Let's see. Okay, so we have iron and aluminum sulfate in water. So is that going to happen? Okay, so we need to find the two metals on the reactivity chart. So we're going to have iron here and aluminum. So aluminum is above iron, and aluminum is not a metal in that reaction. It's a salt. So is the reaction going to go? No. The metal has to be on top. The metal wants to be oxidized more than the salt wants to be reduced. And that's what the reactivity chart is on. Oxidation. So this is going to be there's a lot going on here with the oxidation and reduction. You're going to study that at length if you take 1A, 1B. It's going to be just disgusting detail. You can do labs on it and everything. So oxidation reduction is really an important type of reaction chemistry. Okay. Let's see, it's 11:40, 50. Okay, I'm going to
Um,
I am covering this today. And since we have enough time. Two things on here. One is called solubility rules. It says general solubility guidelines or rules. And the other is this chart I made. Okay. So I'm going to start on double replacement reactions. Okay. So what I've done is I've taken these rules down here and created a chart. And the rules say, you know, compounds of group one elements, blah, 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 are soluble. So you have to, you know, go back, okay, where's group one on the periodic? I bypassed all these rules and made this chart. So it's a black and white chart. If it's black, solid forms. If it's white, no solid. How's that sound? Instead of worrying about the rules. Now, you may or may not have to know the rules for your next class. Depends on the instructor. Totally. So they'll either give you the rules or have you memorize the rules. So, and yes, you're going to have this on the test. Okay, so let's say Silver sulfate. Is that a solid? You find the silver, find the sulfate, and where they meet, is that black or white? Black, so it forms a solid. All there is to using it. Notice a couple things. No matter what you add to nitrate, it's white all the way across. That means nitrates are always soluble. Always soluble. Acetate. Same thing, white all the way across. Vertically, sodium, potassium, white all the way down. Those are also always soluble. And everything else is, it depends on the solvating force of water versus the crystal lattice force. If it's black, that means crystal lattice force is stronger than solvating. If it's white, the opposite. Solvating is stronger. Okay. So double replacement reactions are two salts added together. When I say salts, that means they're dissolved in water. They're aqueous. And we're going to dump them together. When we dump them together, we have new possibilities of hookups. The sodium, not the sodium, the silver now is bonded to the nitrate. And we found the nitrates don't bond with anything. So that's why this is in water dissolved. Sodium, same thing, doesn't bond with anything. It bonds ionically, but not for a solid. Okay, so these are both aqueous. We're going to dump them together. So we have two new combinations. We have sodium chloride and we have sodium nitrate. Well, the sodiums we know are going to be white all the way down. Nitrates white all the way across. So that's going to stay aqueous. But silver and chloride, when they cross, it's a black box. Hence the S for being solid. The sodium and the nitrate are spectator ions. So sodium is always a spectator ion because it's white all the way down. Potassium, white all the way down, so it's always a spectator ion. If the column or row is white all the way across, those are spectator ions all the time. And chloride can be a spectator ion sometimes. When it gets around silver, lead, mercury, it binds up. In fact, in the old days, before instrumentation, we used to do a lot of wet tests to determine what the identity of something. And one of the tests was using silver nitrate. Drop silver nitrate into the liquid. If it forms a white solid, chloride's there, or bromine or iodine, any of the halogens. It was a white test. And then you have to do another test to verify that it's still, in fact, chlorine and not iodine or whatever. Okay, so in a lot of ways, students feel that the double replacement is easier than single replacement, because you have that solubility chart. Now, sometimes there's no reaction at all. If everything is white on the solubility chart, no reaction. Sometimes everything can be black, though. So sometimes you can have a mixture of solids. So if everything is white on there, you will have 4 spectator ions. If only one thing is black on there, you'll have 2 spectator ions. Or if everything is black, you'll have no spectator ions. It's either 0, 2, or 4. Now, I mentioned neutralization earlier today. When neutralization occurs, that's between an acid and a base. An acid's H plus. A base is the opposite of an acid. It gives off an hydroxyl ion, OH. So when H plus and OH come together, it forms water. Unfortunately, in your lab, you'll be doing it on a piece of paper or a laminate. And when you do it, you're not going to be able to see the water form. So you're going to write no visible reaction, but in fact, water's formed. So when H comes together with OH, we form water. And that's an acid-base neutralization reaction. So you end up with water plus salt and lots of heat. Lots of heat. Okay. So when you do a double replacement reaction and something happens, you're going to have to write something called a net ionic equation. Net is the key word there. So what did you make? In the case of so what did we make here? Did we make anything? Did anything happen? What happened?
Silver nitrate and the sodium chloride turned into silver chloride and sodium nitrate.
Yes. So what did we make?
Sodium nitrate and silver.
Right. But did anything visible happen?
There's a solid.
Yes. Silver and chloride come together, it's black. It means it's a solid. So if a solid forms, we need to have a net ionic equation. So what made the solid? Well, the silver and the chloride made the solids. So those make up the net ionic equation. So we have aqueous silver, aqueous chloride forms a solid silver chloride. Sometimes it's called a precipitate. Sometimes it's called a solid. And a precipitate is PPT. And that is precipitate. Yeah, precipitate. And it's a lot of people distinguish between the two, but basically they both look exactly the same. They're both solids. Okay, so when you do a double replacement reaction, first thing is you're going to write the whole thing out. Secondly, you're going to have to write out a net ionic equation. And thirdly, you're going to have to identify the spectator ions. 3 of those. Sometimes there's no net reaction though. Everything is white in that solubility table. You have no net reaction. So you'd write, if there's no net reaction, that's your net reaction, null set. Okay, so let's continue on with this silver reaction here. All right, so we're starting with AgNO3 aqueous, sodium chloride aqueous, gives us aqueous sodium nitrate solid silver chloride. So let's write out the whole thing. Okay, this is called the molecular reaction. XN is reaction. Now, in your next class, you're going to be asked to write out the total ionic equation. So first of all, is this balanced? Yes, balanced is written. Okay, so this is molecular reaction. I'm going to show you the total ionic reaction. And you're not going to have to do one, but you will have to do one in your next class. I'm just going to show it to you so you'll be able to recognize it. Basically, you take everything apart. Okay, so we're taking this silver nitrate apart to silver and nitrate ions. Sodium, sodium, 1 and 1. Chloride, chloride. Just look at the numbers, just like you're balancing any other equation. Okay, so that's the total ionic equation. TIE. ME for molecular equation. Is there a net ionic equation? Yes, solid formed. The NIE, net ionic equation. There's spectator ions. So that's a complete double replacement reaction equations. Now, in here, you're going to be responsible for the molecular equation, balanced, and you're responsible for any net ionic equations, balanced, and spectator ions. Now, individually, these aren't too bad. When you put all these little parts together, though, it gets complex. Not because the little parts are difficult, they're simple, but there's just a lot of them. So there's a lot of places to lose points when you write it, particularly when you write out the total ionic equation. You've got AQs to worry about. Is it balanced? Are the charges correct? A lot of little parts. So there are always a molecular ionic equation involved. No exceptions. On my test, there won't be a total ionic equation required. But you will have, you're responsible for the net ionic equation. In other words, did something happen? Did a solid form, the box black, and then spectator ions. And that's basically it for double replacement reactions. Except for the total ionic equation, most students find they're easier to understand than the single replacement.
If, for example, if for the, by chance you started with a solid and it ended, if it turned into a solid, if it stayed a solid with the things in it be the spectator ions, but if it turned into a aqueous, it would be in the.
No, spectator ion has to be in the left and the right unchanged.
You
So
can
if you-
have this,
Yeah, you can actually.
and that would be in, those would be spectator ions.
No,
If it
It would-
doesn't,
if a solid's involved at all, there's no spectator ions. Only if no solid is involved. Like sodium plus nitrate. White all over the place. Okay, so no solid formed, and spectator ions. So that's why sodium will always be a spectator because it doesn't react with anything. Potassium, nitrate, always a spectator because it never reacts with anything. And then everything else is a mixed bag, depends on what you combination you come up with. Okay? All right, so that's it for today. For lab, today and tomorrow is going to be single replacement. Monday, Tuesday will be double replacement. Both good labs. Students like them.